Hello AP Chemistry students, and welcome to Unit 2. So we're starting off section 2.1 on the types of chemical bonds. Our learning objective for this one is to explain the relationship between the type of bonding and the properties of the elements participating in the bond. So when we talk about bonds in chemistry, we're talking about electrons that are moving between atoms. And these electrons are either going to be shared, where they sort of hover in between the two atoms and exist on both of them simultaneously, or the electrons are transferred from one to the other and stay there. And the main factor that determines how this is going to occur is the electronegativity of the two atoms involved in the bond, specifically the electronegativity difference. And as we recall from previous units, the electronegativity is tied to the size of the atoms. The smaller the atom, the more electronegative it is. And if you remember, this is because of Coulomb's law. The closer the electron can be to the attractive force of the nucleus, the more likely it is to get pulled in. And we know based off of our size trends that electronegativity is going to increase from left to right as the effective nuclear charge increases, and electronegativity is going to decrease as new shells are added and the valence electrons, or the edge of the electron cloud gets further and further away from the nucleus. There's also a cool diagram here that shows it as like a bar chart or histogram. And you can see that it's not like a perfect trend, but you can see overall the trend is increasing electronegativity from bottom to top and increasing from left to right. And you can see here fluorine and oxygen are the two most electronegative elements. So the more similar in electronegativity, the more electrons are likely to be shared between the two atoms. And when electrons are shared like this, we call this covalent. A covalent bond, if you think about the word covalent, co meaning like sort of cooperation, and then valent referring to valence electrons, this refers to the way that electrons are going to be shared between two atoms to fulfill both of their valence shells simultaneously. However, when electrons aren't shared, when the electronegativity difference is great, this bond will be considered ionic. And it's ionic because ions are formed in the process. The electron is completely being removed from one and becoming positive, and staying on the other one, becoming negative. And these are like two ends of a spectrum. So pure covalent is when there's no electronegativity difference and the electrons are shared completely between them. And then ionic is when there's a high electronegativity difference and electrons are completely transferred from one atom to the other. But most bonds are going to be somewhere on this spectrum. Not everything is going to be pure covalent or ionic. There's a lot of stuff in between in this sort of a polar covalent realm. And I'll talk about that in a moment. So when a bond is fully covalent, which technically only happens when you have two of the same element, like the chlorine-chlorine example down here, it is considered to be nonpolar, which means that there's no difference in charge on the atoms in the bond. Usually when something's polar, one side of it is going to become negative and one side of it is going to become positive. And while it isn't completely nonpolar, carbon-hydrogen bonds are generally considered to be nonpolar in most cases, or at least molecules that are made of carbon and hydrogen tend to have nonpolar characteristics overall, even though there technically is a little bit of an electronegativity difference between those two atoms. When there's a moderate difference in electronegativity, a polar covalent bond is formed. So I mentioned earlier that polar refers to charges starting to form on both of the atoms, making a difference in charge between them. And most bonds between nonmetals that aren't the same nonmetal are going to be considered polar covalent. And the electrons in that bond are going to be pulled kind of more heavily towards the more electronegative element. So say you had a bond between carbon and fluorine, the electrons, while technically being in both valence shells, as their valence shells are sort of overlapping to make the bond, are going to be more pulled towards the fluorine in the bond. And because the electrons are going to technically spend a little bit more time on the fluorine than they would on the carbon in this example, or the hydrogen and chlorine example down here, this causes the more electronegative element to gain a partial negative. It's not a full negative charge like a anion, but it has like a little bit of negative quality to it that it didn't have before the bond was formed. And the way that's usually shown is with the lowercase delta symbol. There's this little circle with a little hook on top, and a negative. This refers to partially negative. And the less electronegative atom, the one that the electrons are being pulled away from slightly, or the atom that's not having the electron in its valence shell like with as much time, is going to be partially positive because that electron is kind of pulled away from it, exposing its nucleus a little bit more. And we call that partially positive and show that with the delta plus symbol. When there's a significant difference in electronegativity, which usually occurs when you have a metal and a nonmetal on opposite ends of the periodic table, this generally causes an ionic bond. And the nonmetal will become fully negative, being the more electronegative of the two, and the metal will become fully positive, being something with a low ionization energy that is likely to lose electrons. And there's no sharing of electrons in this case. The metal is going to become a cation and become fully positive and lose its electron for good, and the nonmetal, the anion, is going to gain that electron and keep it for good. And they're going to have a strong Coulombic attraction between them once they become positive and negative, respectively. And there is certain values of electronegativity that cause these different types of bonds, but it can be a little bit blurry sometimes. But you're going to be getting a worksheet on this that is going to be you're going to be calculating electronegativity differences and characterizing bonds using that difference. But that's not the only way to think about it, and I'll talk more about what I mean with that in a sec. So the bigger the difference in electronegativity between the two atoms in the bond, the bigger the dipole. So a dipole is a pair of opposite charges that give the bond electromagnetic properties. And what I mean by that is kind of what I was mentioning earlier, where like even in a non-ionic bond, in a polar covalent bond, when there's electrons being pulled towards one atom and away from the other, one of them becomes negative and one of them becomes positive, and it ends up having two poles, or a dipole, much like the poles of the Earth, which are going to have sort of different magnetic properties. And we usually depict these dipoles as an arrow pointing towards the more electronegative element, or where the electrons are being pulled. So in this hydrogen-fluorine bond, fluorine being the more electronegative element, is going to pull the electrons towards it. So we show the arrow pointing the other direction. And one specific way that these arrows are drawn is with a little like cross through the end. I don't know what the historical reason for that is, but I like to imagine it as like a plus sign on the end, showing where the positive part of the dipole is. So we talked about covalent bonds and ionic bonds, covalent usually being between two nonmetals, and then ionic bonds between a metal and a nonmetal. But what about metals themselves? Metals can also bond to each other, and that's proof that solid metal exists, because those metal atoms need to be connecting to each other somehow. So there's another type of bond called a metallic bond. And in a metallic bond, in a solid metal, the valence electrons are delocalized. What that means is that they're not local to the atoms. So you'll have a couple valence electrons on your metal atoms that just kind of like detach and kind of move in between. So the electrons are like free. And this is often described as a sea of electrons. And you end up having these cations as a result, because the metals are losing the electrons and they're becoming positive, but they're surrounded by this like fluid of electrons that moves between them. And this is also the reason why metals are very conductive. But we're going to talk a little bit more about metals in section 2.4. And that is all for 2.1 for now. I also mentioned that the difference in electronegativity is not the only way to determine the characteristics of a bond. And what I meant by that is sometimes there is sort of values that don't really associate with either being ionic or covalent. Examples like aluminum chloride, where like you might expect it to be ionic because it's a metal and a nonmetal, but it ends up showing more covalent properties. And the best way to actually define something as being covalently bonded or ionically bonded is to actually observe the properties of that substance, because things that are covalently bonded and things that are ionically bonded are going to have different overall properties. But in the absence of data, the value estimation, when you're subtracting the electronegativity values of the two substances, which you'll be doing in the worksheet, is a good estimation of the characteristics of the type of bond occurring between the two atoms. So I will see you in section 2.2.